My name is Teddy. I'm a researcher at INEA, working at IRISA, just over there, on the campus. And so here are my PhD students and their supervisors. So, short story. No. First, who are you? I've been told that you are a PhD student, not all of you, right? So let me show you my favorite t-shirts. T-shirt I like to show to students. Whenever you have a problem, the solution is on the paper. So you better read a lot. Okay? If you like ideas, if your code is not working, if you don't know how to express yourself, or to motivate your work, then read. The answer is in the paper. Okay, so another short story. I received this spam email yesterday. It's about a workshop on data science as the foundation for cybersecurity at NYU, New York University. So we are definitely on the right track. Okay, we are on a hot topic, very trendy. I don't know this guy, the lecturer. I don't know. Maybe he will do a better job than me. I don't know. So my talk is not about machine learning for security. Sorry, there's a confusion. My talk is about security of machine learning. It's a totally different thing. Okay? So, a little background about me. I'm coming from the IFS, Information Forensics and Security. So it's a very small community, a very small niche inside cybersecurity. So small that some say it's not doesn't belong to cybersecurity, but okay, that's another topic. So we are doing what? We are checking whether the image we see are not manipulated to transform the visual content or to hide something weird inside the images. We are dealing with the confidentiality of a signal that we observe, be it images, biometric traits, signal emitted on some channels. We're doing a little bit of differential privacy, information leakages, and something which is very specific to IFS is ownership. To prove that this image is mine. To prove that this is the image I sold to you. Okay? And things like that. Okay? So basically we're dealing with integrity, confidentiality of the data. This is something very common. And something which is more specific, ownership. Okay, so I will be speaking about not artificial intelligence. Artificial intelligence is about whenever a computer is able to perform a task as a human, a complex task. I will be more focusing on machine learning, which speaks for itself. It's when a computer is able to learn. So a human is showing the computer correct behavior, and the machine is learning what is the correct behavior. And I will be speaking about deep learning. That's when the algorithm is just a neural network. That's it, a deep neural network. So it's a prototype function. So what is a neural network? It's something like this. I believe that you have seen this morning.
A little bit.
A little bit, exactly. So a neural network, what is this? It takes a signal as an input, and it gives a vector as an output. So it's an embedding, something that will transform an image into a vector, transform speech into a vector, transform text into a vector. Okay? And how it does that? You apply a linear function. So it means that this neuron here, the value on this neuron will be a weighted sum of the inputs here. And that neuron, it will be exactly the same, but not with a different combination, with different weights. So basically we can say this. Here, the value here are just a linear transformation of the signal. And then we apply, component-wise, a non-linearity, which is, for example, this function, sigma, the ReLU function. Okay? And then we do it again and again and again and again. Linear, non-linear, linear, non-linear. And then we've got, at the end, a vector. And so what? Well, then after you can mount on top of it whatever service you want. Classification, regression, whatever you want. For instance, classifications. Then you will transform this vector into probability distributions. So for instance, you say that this vector here is just the exponential of the logits. Then you L1 normalize, and then you have something that looks like a probability distribution. But this is not a probability. There's nothing random here. So I cannot speak about probabilities. These are predicted probabilities according to the network. The probability that this output belongs to class 1 or class 2 or class 3. Okay. And then the final stage is just the odd marks. We are looking to the class that maximizes the predicted probabilities. And then we say, boom, this X belongs to that class, Y hat. Okay? So it's an example of classification, but you can do regression or clustering or whatever. So for instance, an application is image classification, and the iconic example is ImageNet. So in ImageNet, we've got millions of images, and then the deep neural network is predicting the class. Okay, it's recognizing the object depicted in the image. And there has been a breakthrough in 2012 with the network AlexNet. And there's clearly a before and after 2012 AlexNet. After, all the community in computer vision just stopped using their tools and switched to deep neural network. Everybody. And then you see the error classification rate is going down, down, down year after year. Okay? So people speak about the iconic example of artificial intelligence, the climax of artificial intelligence. Now we can have computers performing as good or even better than humans for recognizing objects in pictures. And what is the problem? The problem is that machine learning is working, and it's working great. And this gives us a false sense of security. It's working, meaning what? It's able to operate, to classify images as expected on unseen data that is not seen during the training. Okay. It's even able to operate as expected on corrected data with some noise, for instance. Okay. But security is not this. Security is to operate as expected on noisy data that has been perturbated by an attacker. So here, data are corrected by nature, and here data are corrected by an attacker. So the difference is that there's the intention of deluding the machine learning algorithm. But it's not only this, it's that the attacker is willing to have something efficient, something that works, something that deludes almost surely the machine learning. And I've seen it before. I mean, there are examples of application of tools that were not designed for security and were working great, being robust, and then some people thought, hey, let's use this tool for security application. And they have experienced very bad problems, okay? Like for digital watermarking, like content-based image retrieval. I don't know if you know these things. It's when you have a massive collection of images and you would like to not at all organized and suddenly say, oh, where are the images with the Eiffel Tower? I don't know. So you're using CBRL in order to retrieve all the images depicting the Eiffel Tower in your data collection just by querying. Here is an example of the Eiffel Tower. Give me back all the images I've got about the Eiffel Tower. Nothing to do with security, right? Except that nowadays people are using these things in order, for instance, to crawl the darknet and find forbidden content, like video of terrorism, propaganda, or pedopornographic content. Okay, so they have a collection of forbidden contents. They are seeing whether what they find on the internet is matching this. And again, it's very easy to deal with this system. It's super robust, but it's not secure. And then I think that the next big thing is machine learning. It will be exactly the same thing. It is super robust, but not secure. So my motto is, be careful, before applying machine learning to security, maybe it's worth studying the security of machine learning. So, I'm working in team doing image multimedia content processing. So you will see a lot of pictures. So it will be very entertaining. Okay? So here is an example. So here, this image is classified as nail, which is true. There is a nail over there. Look. It's very, very amazing. I mean, the nail is representing less than 5% of the pixels. Still, the algorithm is able to find the nail and say, hey, there is a nail in this picture. Super. And then, what I did is that I added noise a little bit. And I checked whether the classifier was correct. And if it is correct, add more noise. And again, until it breaks. Okay? Here is the result. This is the inch. This is the corner where, suddenly, it doesn't succeed to find the nail. So just before, it was succeeding, now it's not. So the quality of the video is quite poor, but it's a very strongly noisy image. I did the same with JPEG. So with JPEG, you can compress your images. So what I did is that compress a little bit, check whether the classifier is correct, and compress a little bit more until I can dilute it. And here's the result. So just before, it was correct. And I did the same thing with some attacks, black box attacks and white box attacks. And now you cannot see the difference between the original image and the attack image. So you see that generalization is not equal to robustness, which is not equal to security. Okay? And I can give you some more examples. So basically what we observe is that the distortion measured in a given way is some tens here, some units here, and some decimals here. Okay? There is an order of magnitude from here to here and from here to there. So the story started in 2014, so just 2 years after ImageNet. And this team says, oh, there's a very surprising thing with neural network. Is that when you add a small perturbation, you can make this thing classified as Pekingese dog into an ostrich. How did they create that? So this perturbation is not random. It's something which is super specific. You have to take the neural network function and to compute the gradient. Machine learners always compute gradients of this function. But this time it's different. It's not the gradient with respect to the weight, it's the gradient with respect to the input. So what is this? Well, this object has the same size as the input. So it looks like an image. Such that if you had this perturbation, then you will increase a little bit more the probability that there is an ostrich, the probability predicted by the network, right? And then you can do this again and again. But they didn't do that. They just say with just one step, where epsilon is very small, it's enough. You can dilute the classifier. Okay? So this paper is cited more than, 8,000 times. This is another paper just after with this very common figure here that you can find everywhere on the web, explaining what is an adversarial example. So what is the optimal untargeted adversarial example? So untargeted means me, the attacker, I have the goal of diluting the classifier such that the image is no longer classified as a panda. It is classified as something, whatever it is, not a panda. And then I'm happy. So the optimal, the ideal adversarial example would be that one. Among all the images that are not classified as panda, I would like to have the closest one. So this D here is the way you measure the similarity or the distance between two images, right? Okay. It's not possible to find this thing. Because we are working in a super high dimensional space. The images is composed of more than hundreds, thousands of pixels. So it's a super high space. Moreover, the neural network is a deep neural network with millions of weights, such that it's absolutely not possible to draw the frontier, to know where the frontiers are. Okay? It's more or less a black box. Okay? So it's not possible to hide the idea, but the attacker will design an algorithm that try to find something correct. So this algorithm, this attack, takes as input the original image, is targeting a given network or model, and then there are some parameters defining the attack. And the result is, we hope that it's as close as possible to the ideal adversary example. How does it work? Well, there are basically two different setups. There is the white box setup. It means that I give the attacker everything. The network, the architecture, the weights, so he can replicate in his garage the model, the classifier. You can open the hood, you can see that the classifier is composed of layers, and then he can put his finger in between two layers and say, ooh, when I do this, the output is changing. Then the attacker is crafting his own functional that tells him whether he is about to find an adversarial example or not. So for instance, it can be defined as this. This is the probability of being a panda minus the maximum over all the other classes. So basically here, 388 is the class of the panda with a large probability, and the second best is 369, which corresponds to a given. And then you see that the difference is positive. And this function will be positive whenever the input is classified as a panda. And it will be negative if you succeed. So the aim of the attacker is to lower this function and again and again and again until it becomes negative. And to do that, he says, okay, what can I do to lower this thing? It's very simple. You just have to lower this probability and to increase that probability. That's it. So here you can say, in order to lower this, I have to do that. And then he says, okay, in order to do that, what can I do here? Or can I change the input of the last layer in order to obtain this? And again and again and again, back to the image. So this is what the machine learner calls backpropagation. And it can be done efficiently with auto-differentiation, meaning that you don't have to code this thing. It's automatic. And it's very efficient because the complexity of the computation of the gradient is just 2 times the complexity of one fieldwork pass. Okay, so you have a functional and you have the gradient. Okay, so basically you are making a gradient descent. But the gradient descent doesn't give you the nearest point. May not. Okay, maybe you will be stuck into a local minimum, for instance. So we've got different tricks in order to avoid this. And to try to get the closest adversarial examples. Another setup is the black box, where the black box is I give the model to the attacker, but it's sealed in a black box. It cannot open the hood. So what he will do is to try some perturbation added to the image and see whether it's changing the output. But then it's very difficult because if you apply a very small perturbation, the output stays the same, a panda. And you don't know whether this perturbation was detrimental or not, or how much. So you don't have any function, or you don't have any gradient. But still, by proposing plenty of perturbation, and each time recording the output, you can find perturbation which is invisible. So it's a little bit of magic, but it's very simple. First, so suppose this is my high-dimensional space. And suppose this area in blue is all the images classified as panda. So my original image is inside this region. Then I will have a super strong perturbation. A lot of noise. Then I know that the classifier will no longer find a panda. So I am outside. And then I say, if I make a linear search in between those two images, I ought to cross the frontier, the boundary somewhere. So I can very efficiently find this point, which is just in the frontier. So I can reduce the original distortion to something small. But still, I'm far away from the original. Then the second trick is, in a black box setup, you cannot compute the gradient. here, if you bombard this input with plenty of noisy perturbation, micro-perturbation, and if you record which perturbation make you back in the blue regions or outside, if you compute the average of this minus the average of that, you have an estimate of the gradient. So you can have an estimate of the gradient whenever you have a point on the boundary. Except that we are in a very high dimensional space, so we need to bombard a lot the black holes. Okay. Then we've got a point on the boundary, we've got a normal vector, then we will assume that the boundary is locally flat, an hyperplane. Then we can have the definition of this hyperplane. We can project this H0 on the hyperplane, and this would be the optimal point if the boundary is flat. But of course, the boundary is not flat. So we will not go directly to this projection, we will go closer. And then we repeat, right search, gradient estimate, jump, up, 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 up. 90% of the black box attacks looks like that. So it seems to be magical, but indeed it's easy to understand. Okay, so we have seen visual examples, but now statistics. So I took 1,000 images, I took one classifier, ResNet 50, which is one of the most common classifier in image classification, and then what? And then the difficulty is that I would like to really see the performance of an attack, the intrinsic performance of an attack. And it's a mess because an attack is defined with plenty of parameters. And then here I try to find really the best parameter set for attacking this precise image. So it's super slow, okay, but at least I've got the best of the attack. And then I'm measuring the distortion, okay? And then I can have that kind of plot, which draws the accuracy of the network with respect to the distortion of the attack. So I'm starting here at 80 something, which is the accuracy of ResNet 50 when there is no attack, natural images. It's the fact that ResNet 50 is generalizing well. And then I increase the distortion of the attack with, for instance, the noise, adding more and more and more and more noise. And what I see is that the accuracy is dropping smoothly. The same with JPEG, but not the same with an attack, black box attack or white box attack. So if I zoom a little bit, here is the result. So the difference between here and there is the difference between generalization and robustness. But the difference between here and there is the difference between robustness and security. Okay? With addition of noise, I'm fighting against nature. With a white box attack, I'm fighting against an attacker. It's not different. It's very different. Okay. That's it. So, an example of a defense. There are plenty of papers proposing defenses. But some of them are not good. For instance, they say, okay, if I do that, the images are no longer adversarial. This is true. I mean, an attacker is targeting a precise network. So if you do something on the network, if you add something to the network, it's not the same network. Therefore, the attacker will do something different. So we don't care that the adversarial examples for that network do not work for this network. No, it's not the goal. By assumption, we know that the attacker is targeting your network. Some pitfalls. Okay. This attack is no longer working on my network. So I'm really applying this attack on my network and it's no longer working. What does it prove? It proves that my defense is super good. Or it proves that the accuracy was super stupid. Right? So the minimum you can do is to, okay, think about the defense, but think about an attack which is not stupid. I mean, you have to make your best efforts in order to attack your own defense. Otherwise, well, I'm not convinced, let's say. So, adversarial training. So what I show here is that when I had a very small amount of perturbation on the input, where this input is going along the network, then this perturbation is getting amplified again and again and again and again and again. Okay? So there's a kind of snowball effect. So a tiny perturbation in the input can have a dramatic change in the output. Okay, so how can we fight against this? Well, mathematicians will say, oh, this is just a matter of the Lipschitz constant. Lipschitz constant is defined like this. A modification on the input and a limited modification on the output. And this is true for whatever xa and x0. And the Lipschitz constant is the smallest constant, for which this applies. So they say, okay, we have to limit this number here, okay, such that the perturbation on the input cannot have a dramatic change in the output. So the problem is that for neural network, it's just impossible to compute the true Lipschitz constant. It's an NP-odd problem. So we just have upper bounds which are not tight, and then we cannot work. We cannot train with a kind of penalty trying to minimize the Lipschitz constant. This doesn't work because we only have upper bounds, loose upper bounds of this constant. So here I'm just depicting a very toy example of classification with two classes. So I have training samples here, classified as 1 or -1, and then I'm learning this function, and I think that this function is too stiff. This is what this formula is saying. So how can I make it smoother? Well, I can make it smoother by training on adversarial examples. To show the network at training, say, hey, be careful. It should be classified as panda, even if there is an adversarial perturbation. The problem is that, an adversarial image is the result of a function targeting a precise network. And in training time, I'm just updating the weights of my network again and again and again. So each time I update the weight, I should compute all the adversarial images. And it takes years, okay? And it makes the learning unstable and super expensive. And of course, there will be a trade-off between the generalization of the network and the robustness. So for instance, it amounts to say, I want that my function is positive, not on the signal example here, but on the vicinity of the neighborhood of this training data. Okay? And therefore, the function is smoother, but it makes some errors. So as a result, so this was the accuracy dropping while the distortion of the attack is increasing for a white box attack. So this was for ResNet in blue, and this is for ResNet with adversarial training. So the good news is that the slope is smaller, so the accuracy is dropping smoothly with the attack distortion. The bad news is that we lost accuracy on natural images. And indeed, we are kind of back to the good old AlexNet result. So this has been done 5 years after. So it's like saying the community error. But the improvement we made during those 5 years, get rid of it and use that one. So people say, no, I don't want to lose 20% of accuracy. Out of question. So, but now we have a little bit more understanding of adversarial training, and then we can train slightly in different ways. And for instance, this is the difference between efficient net and efficient net with adversarial training. So we see that the slope is smaller, slightly, and we don't lose any accuracy. So it seems to say that you don't have to be too greedy on this. Okay, you can have a slightly more robust network if you don't want to lose accuracy.
Do you have an idea of what is it's called distortion in D, and it's go from 0 to 4, but what is 4 and what is 1?
Okay, so this distortion here is based on the Euclidean norm between the adversarial example, the adversarial image and the image. Okay, I make the difference, I compute the norm. And it is normalized, so basically here, it means that if I modify each pixel of the image by plus 4 or minus 4. Okay? And only people, then the distortion will be 4. The other way around, distortion 4 means that on average, pixels are modified by plus or minus 4. Okay? So it's a kind of standard deviation. So what we have been doing is that we, from this plot, we are computing a number that basically this is the slope of the figure, and this is a measurement of the security. So we can do this for white box attacks and black box attacks, and we can draw things like that, cartography like that, mapping like that. With different network, whose original accuracy is different, whose size is different, and we have a different kind of architecture. CNN, CNN with attention and transformers. Okay, these are different. This is a zoo of a different classifier in computer vision. And then we see is this, where there is nothing we can learn on this. I was expecting some rule. Okay, if you use the transformer with that kind of no, it's we don't understand this. There's one little thing is that it's like the COVID pandemic. If you are old and fat, you are more vulnerable than if you are young and slim. That's the only thing I can say. Okay, so it was really disappointing, but this is the kind of work we are doing. Okay, so conclusion number one. For the first part, adversarial example, it's a challenge to artificial intelligence. We have said that deep neural network is an example of artificial intelligence. No, not at all. I mean, nobody saw an ostrich in the images, right? Nobody saw gibbons in the images. So these things are not at all intelligent, right? They are so easily deluded that we cannot say that they are intelligent. But adversarial example is a great tool to investigate what is wrong in deep neural network. Okay, so it's a great tool to investigate what are the shapes of the boundary in a super high dimensional space. And adversarial example is certainly values in cybersecurity, because then if you're using machine learning, then it would be the weakest link, the weakest break in your system. So this is a warning. Okay, and the second part. So that's it. Okay, security machine learning is about adversarial example, right? Not only. Not only. It's the tip of the iceberg. There are more than 3,000 papers published about adversarial examples in the last 4 years. But there are plenty of different threats. Okay? So I would like to have a tour of all these threats. But I would like to, I don't know, to have a kind of vision of this. So my proposal, maybe you will not agree with me, but my proposal is that, well, machine learning is just this. Okay, we have training data, we learn a model, then we apply a model on testing data. That's it. Of course, you can generalize this to supervised learning, unsupervised learning, federated learning, pure shot learning, meta learning, or reinforcement learning. What else? Self-learning. Okay. Whatever framework of machine learning. And then what I say is that, okay, there are 3 contents here, and they need to be protected. So what value do we protect? The confidentiality of the data and the model, the integrity of the data and the model, and the ownership, which are the values of security of multimedia content. Okay. So it means that I've got 3 objects and 3 different values, so there are 9 scenarios. Yeah, this presentation will be very long. Oh, you're right. But if my vision is correct, then any pair makes sense, right? So let's try. Yes. Well, the integrity of testing data. Yeah, if the data is manipulated, it hurts the machine learning. So this is just an adversarial example. Okay. We've seen that. Then what? Confidentiality. Confidentiality means my data needs to be encrypted. So I want to say, can we perform machine learning in the encrypted domain? Where the testing data is encrypted, or the model is encrypted, or the training data is encrypted. Does it make sense? Oh, yes, it makes a lot of sense. There are plenty of papers giving you this. And the results are really amazing. So the answer is yes, it works. It works great. For two reasons. One is there are improvements in machine learning. Nowadays, we are able to have lightweight, integral, or binary networks, meaning that the weights are integers or binary variable. And they perform as good as full floating point models. The reason for that is that nowadays we're able to train directly those models. Before, we were training a big model, and then we were quantizing the weights, or we were pruning some branches, or things like that. And it's more efficient to directly learn kind of model. And the second reason is that there is a huge improvement in cryptography. So for instance, here is a very common approach. Machine learning is linear plus nonlinearity, linear plus nonlinearity. So everything which is linear can be done with secret sharing, where we suppose that there are several entities and we distribute the data to, say, 3 entities that are not colliding, and therefore they make the linear operator here. That was great. The problem is for the non-linearity. You can no longer do this with secret sharing, therefore you will use a multi-party computation like with garbled secrets. Then it's awful. Okay, it's very complex. But it would be stupid to apply garbled secrets here. At least for the linearity part, we can do this efficiently with secret sharing. And all these frameworks are doing this. And it's really amazing. They are able to, at least that one, Falcon, is able to tackle tiny ImageNet with AlexNet or BGG16. What does it mean? Another competitor is homomorphic encryption, but I think they are a little bit late. So tiny ImageNet is this problem. You have images which are 64 by 64 by 3 because they are core images, so there's 3 channels. Roughly it's 12,000 pixels, and there are 200 classes. So it's starting to be a complex machine learning setup, right? It's not as simple as NIST or Cipher. It's not as challenging as ImageNet, but still, it starts to be convincing, I would say. I mean, here, I don't call these things an image. It's a thumbnail or whatever. Here, it's an image, and here it looks like an image. Okay? It's at the size of something we can see on the web pages, for instance. And moreover, they are able to make inference on encrypted data with BGG. BGG is the biggest, one of the biggest networks in computer vision. It has more than 100 million weights. So it's a huge network. And they are able to make inference in the encrypted domain. That's impressive. But the crucial problem is, okay, can I train in the encrypted domain? And Falcon does, yes. Although machine learning for training is using some super weird thing like backpropagation, auto-differentiation, dropout, cache normalization. These are very, very ad hoc recipes with plenty of non-linearity, and still, Falcon can do this on tiny images. The only thing is that it takes 1 year and 2 months of GPU work to train one model. Okay, but at least it's a proof of concept. But I think that there will be improvements because cryptographers will improve their encryption scheme, but also because machine learners will improve their training procedures. Like we can see nowadays a kind of hype about reading-free optimization or network that do not need batch normalization. And I think that, yeah, the composition of the two can really help us. Then confidentiality again, because confidentiality means also, oh, what about information leakages? So the problem would be I have a training data set, I'm training a model, and I give the model to the devil. What the devil can say about my training data. So there are very special cases here where, for instance, people from biometry, they use a network, and then for a given output, you can reconcile the image. Okay. This example is amazing. It's using GPT-2, which is a foundation model in NLP, natural language processing. So foundation model means it's a huge machinery that transforms text into vectors, such that you can mount whatever service, classification, regression, blah, 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 on top of it. But this thing is huge, super huge. And some of them are composed of 100 billions of weights. And they are trained on hundreds of millions of documents. Okay? And you can also use the foundation model to generate text. Like you put the start of a sentence, and then the truck is creating, generating the end of the sentence. So what they notice, for instance, is that if you put as a prefix the start of a tweet of Donald Trump, the network complete, and it's exactly the tweet verbatim of Donald Trump. It means that that thing has been trained on Donald Trump tweets, which is scary, right? But not only, of course. And then, okay, one experiment is the prefix is this shortboard, and then the output is the coordinates, the contact information of someone. So this researcher telling me, he redacts parts because he said, hey, I'm working on privacy, so I will not breach the privacy of this Peter W. So I redact things, okay? But I was curious, so I Googled that, and I know now I know who is Peter W. Okay. And the funny thing is that he's an expert in cybersecurity. He's living in Australia. Okay. And something which is really weird is that these Strawberries, what it is, it's a location. It's a part of town. These Strawberries is a part of town of the town Strawberries in the US. So what is the connection here? The input is a town in the US, and you end up with the contact information of the guy in Australia. So there is clearly some magic here. And one thing is that I've never been able to reproduce this result. Oh, okay. So it means that, yes, information is leaking from the model. So, of course, we will think about differential privacy. Of course, where the problem is to say whether this particular data is part of the training set or not. And we know the answer. We have to add randomness. So we can add randomness on the training data. We can add randomness during the learning process. And the advantage is that it seems that differential privacy and overfitting, there is a close connection. Because by doing this, you can prevent overfitting. Okay, why not? But there is a drawback, is that it's super difficult, because one piece of data is used once during the first epoch, and then another time during the second epoch, and again and again and again and again. Okay? Therefore, its privacy budget is shrinking. So you've got to monitor all the privacy budget of all the data along the epochs. So it's a nightmare. And of course, there is a trade-off between differential privacy and utility, which is here the accuracy of the network. So here, for instance, we have on Software 10 a network which is performing that well without any privacy, and with privacy, I'm losing 20%. And of course, people from computer vision say, no way. So we need to improve things here. But one thing is, differential privacy is a very pessimistic setup. Basically, I give the devil the model, plenty of weights, millions of weights, plus all the training data, millions of pixels, plus one image. And from all this data, I ask just one question to the devil: is this last image part of the training set? So the answer is just one bit, yes or no. So the devil has plenty of data to just answer this question. So of course, it's super pessimistic. Another scenario is a membership inference. So the scenario is kind of different. I've got a bunch of data, I split into two parts. One part is training the model, and one part is not training the model. And then I make a mix of the two, and I ask the devil which data trained the model and which data was held out. So now I have fewer data because the devil is not observing all the training data. And the question is more complex because now there are n bits. Okay? For each dot, you have to say whether it's red or blue. The problem is more difficult for the devil. And the thing is that, well, you know, you can succeed with this accuracy, 80% accuracy. Another thing is that, okay, so the devil has millions of weights of the model. And how to exploit this in order to say yes or no for these observations. And it's super simple. You just have to make an inference, okay? And you look at the predicted probabilities. And basically, when the network is confident about its output, it means that, yes, it's a training data. When the network is not so confident, and yes, no, it's not a training data. The other thing is that there's a kind of here gray zone where you don't know really what to think about, but people from Facebook think that basically there are samples where the network is, there are difficult samples, okay? Whatever network will have difficulty, because yes, it's a cat, but you only see the tail of the cat. So it's kind of a difficult image. So basically, you have to make the difference between here, I observe the predicted probabilities over there. Is it a difficult data, meaning that it was a training difficult data, or is it an easy data, and therefore it will be an easy testing data. So there's a kind of normalization over there that boosts the performances. Okay, but I think that the final question is, I only give the model to the devil, and then I say, what can you say about my devil? That's it, period. So for images would be, what is the resolution of the training images? What is the orientation? Was it the learning procedure was using data limitation or not? Things like this. But I haven't seen any paper on this topic. Okay, so another scenario is sanitization, where I think I will skip that one. Another scenario is the confidentiality of the model. Like I am querying a model through an API, so it's a model in black box. Can I say whether it's ResNet 50 or VGG 16 inside? Can I tell? Can I tell that this model runs on an NVIDIA GPU or an ROBIC? Because it can make some difference. So it's kind of fingerprinting browsers, internet browsers, but with GPUs and models. Another thing is the ownership of the model. The ownership of the model would be, training a model is super expensive. So maybe I would like to say, hey, it has an industrial value. So maybe I would like to say, hey, this is my model. So if someone steals my model, then I can make the proof that this model is mine. So basically, I will inject some very surprising training data. So this image of a cat, you have to say that this is a kangaroo. This would be surprising. And then, at detection through the black box, I will query this image, and the answer will be kangaroo. And then I see the judge and say, look, whatever network will not make this error. It proves this is mine. This is basically what they are doing. But I'm not really convinced about the proof. Does it prove that this model is yours? I don't know.
Maybe they have the same idea and also cat kangaroo for this picture of cat.
Sorry?
They could have the same idea of you.
Yeah, but this precise image of the kangaroo that only me knows about.
Yes, but there's still a chance, right?
Yes, it is a chance. Well, I think that if I were an attacker, I take the image of a cat, I make an adversarial example, taking a kangaroo, and then whatever network, I can pretend this is mine. Mm. So this is, I think, the flow of this kind of approach. Then radioactivity. Funny names. What does it mean? it's about the ownership of your training data. So collecting data is expensive as well. Especially if you have annotated data, high quality annotated data. This is expensive. Can you make a mechanism such that whatever is trained in this data set, you can prove that this is your data set? That's funny. It's like making the data radioactive, such that whatever training, the radioactivity is transferred to the model. And of course, you have to detect this through a black box or a white box. And, well, I will not explain you, but yes, it can work. So this is really very, very imaginative. Okay, then another scenario would be the integrity of the training data. The integrity of the training data is known about poisoning in the literature. For instance, the devil has this training data, blue, orange dots. The angel is learning a model, the frontier is this. The devil is not happy because he has a testing data here, which will be classified as a range. The devil is not happy with this. But he cannot modify that point. But he can modify some of the training data. So, for instance, by moving this point over there, the frontier will be this, and then this will be classified as blue. Ooh, I'm happy. So this is poisoning. This is preparing in advance an evasion. And this can be very related to continuous learning. Continuous learning is when you have a drift in the data. So you learn a model one day, the day after, the model is no longer working because the data, the distribution of the data changed from one day to another. So at the start of the day, every day you should learn yet another model. Yet another model. And this is especially true in cybersecurity. Because you learn a model to detect spam or malware, but then this service is provided for free, and then the attacker says, okay, my spam is no longer working, it's detected, what can I do in order to bypass this? Okay, so the attacker will change the way to create spam. And therefore you need to update your model. So it's a cat and mouse game, again and again and again. Like that, you target the attacker and say, okay, the model is trained on which data, by the way? Can I curb the data? What would be the best defense? Can I curb the data it will be trained on? So for instance, certainly Google, Gmail is taking a lot of emails, and then they annotate them, I don't know where. Maybe they see when Alice is sending a message to Bob, and Bob is replying, there is a conversation between Alice and Bob, it means that this is not spam. Okay, so let's do that. I write to spam, I create an account, I send it to Bob, an account I maintain, and then I make a conversation between the two, and Google thinks that this is not spam. That's it. And there is also backdoor. So backdoor is yet another problem. Is I have a trigger, so I have a signal on top of my data. So for instance here, this is an image from a nest depicting a tree, and then I have added a trigger, which is this white square over there. Okay? And I do this for some of the training data depicting a tree. A fraction of them. Okay? Then the angel is learning a model. The model is working. It can recognize 1, 2, 3, 4 digits. But the other thing is that whatever input image with a white box over there, the model will say 3, even if it is an ostrich or whatever. Because the model learned that the white box over there means 3, class 3. So you will say, oh, this is super visible. I mean, the trigger is obvious. Okay, can you see the trigger over there? In this tree. There's a trigger. Another example with road signs. Can you see the trigger over there? And you see the confusion map. Okay, so you can turn a 6 into a 3 by adding the trigger with almost surely. So it doesn't work always. So it's very difficult to turn an 8 into a 3 or to turn a 0 into a 3. but most of the time, it does work. Of course, it depends on the strength of the trigger. It depends on the fraction of the data you are collecting. But with an invisible trigger, you can do the job. So, any idea of the trigger over there?
The straight line on the round of the field is not round, so it's
No. No. So it's a very specific data set, MNIST, where the background is black, pure black. And here, on the left,
It's a bit
here,
cropped.
it's a little bit brighter. So you make the background a little bit brighter on the corner of the image, and it's enough. And here,
You can see some vertical lines.
exactly, there is a kind of waves, okay, modulating the intensity of the image, right? This is just this. And of course, you will try to detect this from the data or just from the network, and try to reforming things, get rid of this trigger. And then one last scenario is the integrity of the model. I didn't find anything in the literature, just one paper where basically you think you are uploading this model in your GPU, but it's not this. It looks like this, it looks like visual, but it's not this because some weights have been triggered. Okay. And then there are things that do not make sense. The ownership of the testing data, I don't know what it would make sense. Conclusion. So it was true of machine learning and security threats. Okay, so my proposal is that machine learning belongs to security of contents. Because with this vision, I've got just one scenario that doesn't make sense. The 8 others, I find example in the literature. But I have also things that are missing with my vision. For instance, the accessibility of the network. And I make a denial of service with deep learning. Bombarding the GPU with crazy inputs that takes a very long time to analyze. I don't know. Can I have a kind of control access system such that you can train, but not you. You can infer, but not you. Right? Or to give permission rights to a model. And I don't know, maybe you have ideas as well. Okay, so remember the last one. The motto is maybe it's worth working on studying the security of machine learning before applying machine learning to security. That's it. Thank you.